Yes, hello and welcome to CM Educators with Malim Juma Ogutu. You are welcome to this YouTube #1 YouTube channel. Like, subscribe, share, and don't not forget to comment. So today we are beginning on air and combustion. So we say that air sustains life on Earth, where living organisms need air for respiration. Uh, Plants being among the living organisms, they need air for photosynthesis. Now, photosynthesis is the process where now the plants make their own food, so they need the air in this process. So air is required for combustion of fuels to give energy, it's required in the combustion of fuels to give energy. So let's go ahead and look at the composition of air. So air is a mixture of gases. Air is a mixture of gases. It's made up of different gases, one of them being nitrogen, that now takes up the highest percentage of all the gases in that mixture. We have oxygen, part of the mixture. We have carbon dioxide. We have water vapor as also a part of the mixture of air. So we are saying that air is a mixture of gases such as oxygen, nitrogen, carbon dioxide, and water vapor. So we have a table here that shows the approximate percentage composition of air for each of these. So you have nitrogen that now has 78.1% of the air. We have oxygen that has 20.9% of the air. We have carbon dioxide that has 0.03%. Have noble gases that has 0.97%. Water vapor and dust, they are variable. Water vapor and dust are variable. So we have an experiment that now to determine the percentage of air that supports combustion. The percentage of air that supports combustion. So now the procedure, we put dilute sodium hydroxide solution in a trough. We place a small candle on a cork and float it on the solution. Now remember, we are putting sodium hydroxide solution in a trough, then a small candle we are putting it on a cork and placing it to float inside the solution that we have. So we cover with a glass jar, then we mark on the gas jar the level of the solution. So now we label the level of the solution before the beginning of the before we light the candle. Then we measure the height of the air column and record it. We remove the jar and then you light the candle. Then we gently cover the burning candle with the gas jar. We gently cover the burning candle with the gas jar. So after the candle has gone off, we leave the apparatus to cool to room temperature. Then we mark on the jar the final level of the solution. Remember now, we are determining the percentage of the air that is used in combustion. Then now the final, after we have waited for the apparatus to cool, we measure and record the height of the air column once more again. Then now we remove the jar and measure the changes in height. Then we record our observation. So after having carried out that experiment, you'll have now the measurements that now you will obtain after the experiment has been done. Remember now, you started with a solution inside a trough, then you placed a candle on a cork, then this candle on a cork with it is floating over the solution. Then now we are covering the gas jar. You are covering the candle with the gas jar. Then we measure the height of the solution before the experiment, so that then after having measured now the level where the level of the solution is on the gas jar, we remove the gas jar. We then light the candle. Then we carefully cover the candle. Then again we measure the height of the solution after the candle has gone off. After the candle has gone off. Now, this is how the setup of the apparatus will be. Now, this is our solution. This is the sodium hydroxide solution that we have. Now, this is the cork. Then, on top of the cork, we have a candle. So we are saying that we cover the candle with a gas jar before we light it. Then after having covered it, we mark now where the solution is on the gas jar. After that, we remove it, then we light the candle. After I have lit the candle will burn for some time, then go off. After it has gone off, we mark. After it has gone off, we mark now the level where the solution is. Then we wait after some time. When the apparatus have cooled, then we remove the apparatus. Then now we measure. We now measure the change in the level that has happened. So note that a thin candle of length about 3 meters produces better result in the experiment above. So we use a candle of length 3 centimeter that produces better result in this experiment. So now we go ahead and discuss the observation that we make out of this experiment. So the candle burns for a while, then goes off. As the candle burns, it uses up the active part of air in the fixed amount of air enclosed in the gas jar. Remember now, as we after having lit the candle, when we carefully covered the candle with the gas jar, we covered it inside there having a mixture of air, and now the part of air that supports combustion was also inside the mixture of air. So now after it has been used, the candle will go off because now we don't have a part of air that now supports combustion. So after it has gone off, this leaves a partial vacuum in the gas jar. So greater atmospheric pressure acting on the surface of the sodium hydroxide forces the solution to go up. So now the solution goes up to cover the part of the mixture of air that has been used for combustion. For a little while that the candle was on. So the following are the sample results for a similar experiment. So now these are the sample results of the experiment. So the height of the air before combustion, the height of the air column before combustion was 16 centimeter. So the height of air column after combustion, it is 12.9 centimeter. So now the level of water, the level of sodium hydroxide before the experiment now is 16. It is 16 centimeter. Then now after having carried out the experiment, we'll find out that now the sodium hydroxide has gone further to cover the part of to cover the space that has been left by the air that was used for combustion. So the height of air used during burning, it will be, we subtract 16 centimeter, we subtract 12.9 centimeter from 16 centimeter, we get 3.1 centimeter. So percentage of air by volume used will be the height of air used over the initial height of air multiplied by 100 to get the percentage, where we'll get that the percentage is 19.375%. 19.375%. But now you can see that this is now less than what we expected. So it means that in our experiment we had some mistakes, or we had some errors that could have now caused for us not to get the value that we expect. So combustion or burning is a process in which a substance combines with oxygen in production of heat. Combustion or burning is a process in which a substance combines with oxygen in production of heat. So the part of air that supports combustion is active air, and the active part is oxygen, which forms about 20% of dry air by volume. So the part of air that remains in the gas jar does not support combustion. Remember, that's the reason as to why the candle goes off, because now the remaining part of the air inside the gas jar cannot support combustion. So the component of air that is inactive is mainly nitrogen. So the highest percentage of the mixture of the air that remains inside the gas jar now is mainly made up of nitrogen. So the experimental result is not the same as the theoretical value of the percentage of oxygen in air by volume. So this due to the experimental error. So that's why I have said that now the values that we have, the results that we are getting, we can see that it's not from the theoretical one. So from the theoretical, now after having carried out the experiment, you can see that now the value from what we expect, they are different. So this may result from one, sodium hydroxide solution may not absorb all the carbon dioxide gas. Remember now, sodium hydroxide solution absorbs carbon dioxide gas. Now the carbon dioxide gas puts off the candle. It puts off the candle. So the function of sodium hydroxide solution in this case is to now absorb carbon dioxide, so that now oxygen can actively be used in combustion. That's the reason number one that can cause the error in this experiment. Number two, that now that the error that can cause us not to get the results that we expect. The sodium hydroxide solution may not absorb all the carbon dioxide gas. The second error that could have happened, the candle may go off before all oxygen is used up due to the buildup of carbon dioxide levels. So dilute hydroxide is preferably used instead of water to absorb carbon dioxide that was initially in the gas jar and that which is produced during combustion. And then now heating causes expansion of the gases. Therefore, the apparatus should be allowed to cool before the final reading is taken. So that's why we say that we take the reading after the apparatus have cooled, because now remember we are heating, and heating now of increases it causes the expansion of gases. Therefore the apparatus should be allowed to cool before the final reading is taken. So that's why you say that we wait for the apparatus to cool. So we know that for this experiment, the combustion tube can be made from an ignition tube. We can also make the combustion tube from an ignition tube. So another experiment that we have to carry out. Before we carry out that experiment, you have a caution that we always handle the glass wool with a pair of tongs. So we have an experiment to carry out, but before we carry out the experiment, you have a caution to always handle glass wool with a pair of tongs. So the experiment we have is to determine the proportion of air used when copper is heated in a fixed volume of air. So the procedure: we pack copper tannings in a long hard glass tube about 6 cm long. We connect the tube with 2 glass syringes, with one syringe containing a specific volume of air while the other is empty. So now we are having 2 syringes. One is empty and one is containing specific volume of air. One is containing specific volume of air. So you have syringe air. We label them A and B. So you have copper turnings. Then we have a heat-resistant plastic tubing. We have loosely packed glass wool that we have said. Now this glass wool, we handle them using a pair of tongs. So then we have combustion tube. So we heat the copper turnings until they are red hot. We heat the copper turnings until they are red hot. We slowly pass the air from syringe A through the hot turnings to syringe B and back. To syringe B and back. So we repeat this process while heating the copper turnings until new volume of air in syringe A is constant. Until a new volume of air in syringe A is constant. So you allow the glass tube to cool and record the volume of the gas in syringe A. After having now carried out the experiment, we discuss now the observation that we make from this experiment. So copper is a red-brown metal. And when it is heated in air, it turns black. When copper is heated in air, it turns black. So this is because copper combines with oxygen to form black copper 2 oxide. So it combines with oxygen to form black copper 2 oxide. So we have here a word equation that now represent this reaction. We have copper being heated, where it reacts with combines with oxygen to form copper 2 oxide. We say that copper itself is red-brown solid, oxygen is colorless gas, and now they combine to form copper 2 oxide, which is a black solid. They form copper 2 oxide, which is a black solid. So the following are sample results for the experiment. So the volume of air in syringe A before heating, we say now we have fixed volume. You have 7.5 cubic centimeter. 7.5 cubic centimeter. Then the volume of air in syringe A after heating is 6 cubic centimeter. Remember now the volume we reduce because now the active part of air is being used in heating. Is being used while copper is heated. Is being used to combine copper. Copper combines with that active part of air to form another product. So the volume of air used up during heating, it will be 1.5 cubic centimeter. It will be 1.5 cubic centimeter. So now to calculate the percentage of air used will be volume used during heating over the original volume of air multiplied by 100%. Where now in our case we found out that the volume used during heating, it is 1.5 cubic centimeter divided by 7.5 cubic centimeter multiplied by 100% to have 20%. So about 20% by volume of air is used. So is used during combustion, and 80% of air is air left does not react with heated copper. So remember now in the syringe we had a fixed volume of air. Now we are heating the copper turnings. The copper turnings now they are hot. Then air is inside a syringe where now the active part of air, that is oxygen, now will combine with copper to form now a new substance. Remember now inside this one syringe we had a fixed amount of air. Now and on the other end we are now heating copper tannings. So the hot copper tannings combine with oxygen to form copper 2 oxide that now is black. So in this experiment, the glass wool plug is used to stop the copper tannings from being sucked into the syringe or in the syringes. So it prevents copper tannings. Remember now we are in one syringe we have a fixed volume of air, and now we are introducing it, passing it through the combustion tube to the other syringe and again back repeatedly. We are doing this repeatedly, so this prevents the copper tannings from being sucked into the syringes. So the air is passed repeatedly over heated copper to ensure that all oxygen in the syringes and in tube is used up. So the air is passed slowly to allow enough time of contact between the reactants. So the gas left in the syringes does not react with copper. It is mainly nitrogen, because the highest percentage of air is made up of nitrogen, almost 78%. So in this experiment, the possible source of error in this experiment include the air initially present in the tube is not accounted for. Remember now, we have just accounted for the air inside the syringe, that now we had a fixed volume, a specific volume of air that now we had in the syringe. But now we have not accounted for the air inside the tube. That air is not accounted for. So another possible error is there is a possible leakage of air. There can be a possible leakage of air. Then not all oxygen may have been used up. Not all oxygen may have been used up. So those are some of the possible sources of error in this experiment. So another experiment is to determine the percentage of air used when iron filings rust. The percentage of air used when iron filings rust. So the procedure, we wet a measuring cylinder. And sprinkle some iron filings on the wet surface. We wet a measuring cylinder and sprinkle some iron filings on the wet surface. Then we remove the excess iron filings. After wetting and sprinkling the iron filings, we remove the excess iron filings. Then we invert the measuring cylinder in a trough of water. Then we read the volume of air column in the measuring cylinder. So the setup is left for about 48 hours. After 48 hours, read and record the volume of air column. Then now we record our observation. So in this case, we are now inverting the measuring cylinder inside water after having sprinkled iron filings. Now as we are beginning the experiment, we take the measurement at the level of water where now it is, and then also after 48 hours we also take the measurement where now the water level is. So after those 48 hours, we'll see that now the water level has raised inside the measuring cylinder, because now the active part of air has been used to react with the iron filings, so that the iron filings will have rust. The iron filings will corrode. So the corrosion, corroding of the iron filings uses up the is aided with the active part of air, which is now oxygen. So after having our observation, we have the discussions of the observation that we have. So the measuring cylinder is made wet to ensure that the iron filings stick onto the wet surface. To ensure that the iron filings stick on the wet surface. So when iron filings are left for 48 hours in the measuring cylinder, a brown coating is formed on the filings. A brown coating is formed on the filings. So the brown coating is rust, where now rust is a compound of iron and oxygen. It's a compound of iron and oxygen. So during rusting, oxygen is used and therefore water rises up in the measuring cylinder to replace the volume of air used. Remember now, inside the measuring cylinder, we had a mixture of air and the active part of air has been used in rusting. Now there is a vacuum that is left, that now the water is rising to cover up the vacuum that has been left after the active part of the mixture has been used in rusting. So about 20% of air by volume is used during rusting. So avoid getting in contact. So that is what happens. So the water level rises because 20% of air has been used in rusting. So another experiment also to carry out. And before we carry out the experiment, we have a question: to avoid getting in contact with phosphorus or inhaling its fumes. To avoid getting in contact with phosphorus or inhaling its fumes. So the experiment is about to determine the percentage of air that is used when white phosphorus smolders. When white phosphorus smolders. When white phosphorus smolders. So we are now determining the percentage of air that is used up when iron or when white phosphorus smolders. So the procedure: we invert an empty measuring cylinder in a trough of water. We invert an empty measuring cylinder in a trough of water. Then we record the volume of the air column. We record the volume of the air column. So we cut a small piece of white phosphorus under water. We cut it under water. So we cut it under water to prevent it to react with air. To prevent it to react with air underwater, we attach the piece of white phosphorus to the end of a piece of copper wire. We attach the piece of white phosphorus to the end of copper wire. So remember now, at first, before we begin the experiment, we inverted the measuring cylinder inside the trough so that we determine the amount of air inside the measuring cylinder. Then now we cut a piece of phosphorus underwater. Then we attach it inside the measuring cylinder using a copper wire. So we leave the setup overnight and record the volume of air column. So we record our observation at the end of the experiment. Now from the observation we make, we go ahead and have some discussions. So yellow and white phosphorus smolder in air. This is because phosphorus reacts spontaneously with oxygen to form a mixture of oxides. So it forms a mixture of oxides. So this explains why phosphorus is stored underwater, as it does not react with water. So that's why we say that we are now cutting it underwater, because it does not react with water and we don't want it to react with the air before now the experiment that we have. So it does not react with water. So the reaction can be represented by the following word equation. We have now phosphorus react with oxygen to form phosphorus 3 oxide, and also it forms phosphorus 5 oxide. It forms phosphorus 5 oxide. So after 24 hours, the water level inside the measuring cylinder will have risen to occupy the volume of oxygen used up. Remember now, the active part of air, which is oxygen, has been used up to react with phosphorus. Now there is a vacuum inside the measuring cylinder. Now the vacuum is occupied by the water, where now the water levels increase inside the measuring cylinder. So the difference in volume can be used to calculate the percentage of oxygen. The difference in volume can be used to calculate the percentage of oxygen by volume in air. The percentage of oxygen by volume in air. The percentage of oxygen by volume in air. So the white phosphorus should not be allowed to come into contact with the walls of the measuring cylinder because it stops smoldering. So when now we attach the white phosphorus, it should not be allowed to come into contact with the wall of the measuring cylinder, because now when it comes into contact with the measuring cylinder, it will stop smoldering. And now when it stops smoldering, not the entire of the air could have been used. Not the entire of it could have been used. Then we go further to another experiment. How can the presence of carbon dioxide and water in air be established? So we want to see how we can establish the presence of carbon dioxide and water in air. So we start with the how to establish the presence of carbon dioxide, where now we have the procedure. We place 2 cubic centimeter of fresh calcium hydroxide solution, which is also now known as lime water, in a boiling tube. Then we pass water slowly. We pass water slowly from a tap into an aspirator. Then we record our observation. So we have an aspirator that now, then we have a calcium hydroxide solution. We have calcium hydroxide solution. So we are saying that we are passing water from aspirator. In the second experiment, we pack the bottom of a U-tube with an anhydrous calcium chloride. We pass air through the U-tube by means of an aspirator or a suction pump. Then we also record our observation. So air, we are passing it through a U-tube that has anhydrous calcium chloride. Then that air proceeds to an aspirator B that has a tap. So we note that a deliquescent substance is one which absorbs water from the atmosphere and dissolves. A deliquescent substance is one that absorbs water from the atmosphere and then is dissolved. So from the observation that we make from the experiment, we go ahead to make our discussion. So water is allowed to flow into aspirator A to drive out air that could have been inside the aspirator and bubble it through the calcium hydroxide solution. So now here we are bubbling it. The air goes through, is getting out now to the calcium hydroxide solution. So remember, inside the aspirator we had air inside. So we are allowing water inside so that the air is driven out. It's being driven out into the calcium hydroxide solution. So when the stream of air is passed through the calcium hydroxide solution, a white precipitate is formed. So a white precipitate is formed that indicates carbon dioxide is present in air. So now calcium hydroxide forms a white precipitate when carbon dioxide is passed into it. So this shows the test of the presence of carbon dioxide in the air. Shows the presence of carbon dioxide in the air. Now to the second experiment, where now water is allowed to flow out of the aspirator B in order to create a suction force which draws air through the U-tube. Remember now, the U-tube is connected to the aspirator B that has water. This aspirator has a tap, so we are allowing the water to get out of this aspirator B so that there is a suction force that is created in the U-tube. So through the U-tube we have a suction force that now draws air inside to come and occupy the space, the vacuum that has been left inside the aspirator B. So anhydrous calcium chloride is a white solid. When air is passed through the U-tube, the anhydrous calcium chloride absorbs water vapor from the air and becomes wet. So it may form a colorless solution depending on the amount of moisture in the air. So substances which absorb moisture from the air to form a solution are called the liquescent substances. So remember, we said that the liquescent substances, they absorb water vapor or moisture from air and they dissolve. So apart from the anhydrous calcium, we also have other substances such as anhydrous iron 3 chloride, that is anhydrous iron 3 chloride. We have magnesium chloride and zinc chloride. So those are some of the substances that are deliquescent. Then we go further, we look at fractional distillation of liquefied air. Fractional distillation of liquefied air. So as already established, air is a mixture of many gases and it can be separated into its constituent gases by fractional distillation. Remember now we looked at fractional distillation as a means of separating mixtures, and fractional distillation we can use it to separate air as a mixture. So the air is first purified by passing it through filters to remove dust. Remember now air is a mixture and it also has dust. So now we have to pass it through filters to remove dust. So the dust-free air is then passed through a solution of concentrated sodium hydroxide, where I said now sodium hydroxide absorbs carbon dioxide gas. So now after having a pass through concentrated sodium hydroxide to remove carbon dioxide, the remaining part of air is now carbon dioxide free. So the remaining part is then cooled to negative 25 degrees Celsius to remove water vapor, which now solidifies out as ice. So the remaining part is then compressed to a pressure of 200 atmospheres and allowed to expand. So repeated compression and expansion of air cools it to liquid at negative 200 degrees. Now the air is cooled to a liquid at negative 200 degrees. So you have here a diagram of the process that now we take this air through. So we have air going through a filter to remove dust. So from that we take it into an intake pump. So dust-free air is taken is passed through sodium concentrated sodium hydroxide solution. So remember, concentrated sodium hydroxide solution is used to absorb the carbon dioxide gas. Now this air free of carbon dioxide is now cooled to negative 25 degrees Celsius to remove water, where now it solidifies and gets out as ice Now this air is now compressed. Remember, now it has no water vapor. It's now compressed. So the expansion compressed then allowed to expand, at 200 atmospheres. Then it is cooled to negative 200 degrees Celsius. Now it comes out as liquid air. Then now is taken to the fractional distillation chamber. Inside the fractional distillation chamber, now air, a different fraction or portions of air begins to come out at different degrees. The first one being a nitrogen that comes out at negative 196 degrees as the first portion. We have the second one, which is argon, at negative 183 degrees. Then lastly, we have oxygen at negative 183 degrees. So the liquid air consists of oxygen, nitrogen, and noble gases. Since these gases have different boiling points, they can be separated by fractional distillation. So liquid oxygen boils at negative 183 degrees Celsius, and nitrogen at negative 196 degrees Celsius. So we are saying that nitrogen distills out first. So the first portion to come out, we are saying it is nitrogen because it has a lower boiling point. Now the boiling point of nitrogen is lower compared to the other portion. So that's the first portion that we collect at negative 196 degrees. The other gases made of mainly argon boils at negative 186 degrees. They form the second fraction. Now the second fraction, we are having argon. So the argon can be separated from oxygen by further distillation. So this process is known as fractional distillation of liquefied air. Fractional distillation of liquefied air. Remember, now we began with air as a mixture having dust, passed through filters to remove the dust, passed through concentrated sodium hydroxide solution to remove carbon dioxide. Then it is cooled to remove water vapor. Then compression and expansion to make it liquefied. Then now we are boiling to have it come out in different portion because of different boiling points.